Hey folks, Azure Cosmos DB TV, episode 99. We're almost at 100. And for our last double digit episode, I've got our old friend Nick Laren, who's back with us. Nick, how are you?
I'm good, Mark. How are you?
I'm doing great. Thank you for joining us on episode 99. You will forever be able to say I was on episode 99 of this show. And I'm glad to have you with us
Yeah,
this week.
certainly. Thanks for having me. Hello, everybody. Today, we're going to talk about handling hundreds of terabytes MongoDB workloads with our product, Azure Cosmos DB for MongoDB vCore. Specifically, what do one need to handle such a large workload? If the tens and hundreds of terabytes, which is quite a large workload for a MongoDB workload. So here are kind of the key things. You need a multi-shard cluster because no single node is going to handle such a workload in terms of size and most important performance. You need to have large storage per shard because the smaller is the storage, the greater is the number of shards that you would need to have to handle that workload. And of course, you need a number of fundamentals. The list keeps going. However, what we observed everybody needs are high availability. Everybody cares about availability, right? And people need disaster recovery and read scalability. That's your cross-region replication. So we're going to talk about all of it today.
That's
Let's get
awesome. I got a ton of questions, but I think you're going to get through them, or you'll answer them kind of preemptively. So I'm going to hang back. I'm going to let you talk, but you know me, Nick. I might interrupt.
always welcome.
Okay.
These are good interruptions. Questions
Okay.
are more than welcome.
Awesome.
So multi-shard clusters. Uh, how should we wrap our heads around multi-shard clusters? So first of all, most of the MongoDB workloads, and probably I would go as far as to say most of the databases in the world are smaller ones, and they usually do not require multi-shard or multi-node configuration, just because you can comfortably feed that workload on a modern single node database. You don't need to deal with the complexities of the distributed database. It would deliver you the performance that you need. There is no need to go any further. That said, in today's world, there are more and more workloads that are getting out of the limits of the single node, and that's what we're talking about today. So these workloads are not trivial. They require some thinking and some planning on top of your general knowledge of your database and your workload. So it starts with how many shards do you need? So once you realize that single node is not delivering the performance that you need, or size-wise, your workload is about to get way larger than single node can handle, you need to decide how many physical shards you need to handle your workload. Today we provide up to 10 physical shards that covers absolute most of MongoDB workloads in the world. And with the 32 terabyte per single physical shard, it is 320 terabytes of aggregated cluster storage. Because we deliver 20,000 IOPS per 32 terabyte storage, it is 200,000 aggregated IOPS on the cluster. That's a lot of power that
Yeah.
you can get just with a few clicks in Portal.
That's an amazing amount of IOPS you've got. Is there any way to kind of put that into kind of practical terms? Like how much data can you ingest per second if you're running 10 physical shards kind of at the biggest? I'm guessing these shard sizes with their compute and IOPS are graduated in terms of kind of the size of the compute that you're adding on. Is that correct?
Yeah, that's correct. So that's actually a good question because all of this power is required not only for running the workload, but you need to ingest that a lot of data. Of course, there are kind of different ways of doing that, and migration probably is the whole topic that we can dedicate another episode to. But briefly, there are tools that we're supporting and providing for different migration scenarios. Databricks is one of them. So we recommend to get your data in the same region where your MongoDB vCore cluster is, and then use these tools to ingest and into your cluster. Make sure that your tables are distributed. We're going to talk about that in a second, about the sharding the collections in MongoDB workload. And of course, the general recommendations, they do apply, like do not create indexes until you finish the ingestion and so on and so forth.
Mhm.
But yes, the number of physical shards, of course, helps you with virtually all kind of overhead on the cluster, including ingestion, ongoing queries, and things like index creation.
Got it. Yeah. All right. Sounds like you were pining for coming back for an episode 100 is what I was hearing there on
That
migration.
that's quite a possibility.
Okay. I don't know if we'll get you on exactly 100, but definitely soon after. I think that'd be a great topic actually for folks is, hey, how do I get all this data in? And then this obviously ties in really good to it. So fantastic.
Absolutely.
Okay.
So let's get on. So what else do we need to think about when we realize that we need a multi-shard cluster for MongoDB workload? So each physical shard in a cluster on MongoDB vCore and Cosmos DB has the same compute and storage configuration. So there is no complexity related to trying to decide how much compute and storage I need for individual nodes and so on and so forth. It is just one decision, one basically uh, one run of your workload to decide how much compute and memory and how much storage do you need for the nodes to deliver the performance that you need. So back to my earlier point, the performance is the key for all of these workloads. So basically that determines a lot of things. For instance, how much compute do I need to have on this cluster? If certain level of compute, number of vCores, and gigabyte of RAM deliver the performance that you need, you don't need any increases. You just go with that. And if your workload requirements grow over time, you can easily upscale compute on your cluster. Now switching to performance improvements, what we discussed with the multiple nodes, the high concurrency is there by definition, and their faster execution times just because the workload is distributed on multiple nodes, and now execution is done in parallel for those queries that can be parallelized. The last key thing that I wanted to mention related to multi-shard clusters, that there's a consideration, what is the number of physical shards, the nodes in your cluster versus size of the individual shards? Because with a smaller storage, you can have more physical nodes, and with a larger storage, you can decrease the number of physical nodes and number of compute nodes that you have in your cluster. So spoiler alert, you can decrease significantly the cost of your cluster with the larger storage. We're going to talk about it in a second. And here we're just quickly looking at a very basic diagram, which is showing a cluster, MongoDB cluster with two shards. So it's one of the examples of multi-shards. Two shards already count, and you can have up to 10 to remind you. This cluster is in the same region where your application is, that is doing the reads and writes using the connection string. So application doesn't need to know anything about the complexity of the cluster. The size of it is kind of two nodes. It just has one endpoint to connect to. Connection is basically to a MongoDB database. That's how the app is seeing the very complex cluster. It is just a simple MongoDB database, the same as it would be anywhere else. And all of that, of course, in one Azure region to save on the latency and not go, especially for the writes, not to incur the latency between the regions. So that's to put in your mental model how MongoDB vCore cluster looks like in relation to your application in Azure region. And I wanted to just briefly mention what sharding your data looks like with MongoDB and MongoDB vCore in particular. The few very simple steps. You just go to your database and you enable the sharding in your database, and then in your collection, which I call just sharded collection in this example, then you execute just one command to shard this collection. And you need to decide on a shard key. And that's basically it. After that, you can continue ingestion of the data as you would do with any other unsharded collection.
Uh-oh. I think you're frozen there, Nick.
That are related to the sharded.
Oh, there you go. Sorry, I had a little hiccup on the connectivity there. Hopefully we good in the recording. I got a question. I see your shard collection database command there with hashed. Does that also imply that we support range-based sharding as well?
So we support the value should be hashed, and that's kind of we do not offer anything that MongoDB is not kind of offering. So it's not about us offering something on top
Oh, I
of
see.
the MongoDB standard offerings. It is us using the MongoDB core functionality and just applying it to the clusters that we deliver in our managed service.
Oh, got it. So that probably should have been my first question. Does native Mongo support hash and range-based? I think your answer is no, but the database command there, we obviously are want to be API compliant there as well, and it just happens to have a sharding type there with hashed in it. So it sounds like they don't support that. We support what they support, but the command makes you specify hashed.
Right.
Okay, makes sense.
Okay, go into the large storage. So the next one is the next kind of logical stop in your journey for your large workload is the uh, how much storage can I enable on my single physical shard. Uh, we currently support up to 32 terabyte per shard, and to remind you what we just talked about, each physical shard has the same compute and storage configuration. So you deciding how much storage you're gonna have per physical shard, and then how many shards do you need. Um, if you have tens of terabytes of the workload, this is usually means that you would need the multi-shard configuration, even just by the size. And that's just in Azure because industry standard uh, storage size for MongoDB solutions on the market is usually limited by 4 terabytes per physical shard.
Mhm.
So in case of Cosmos DB, you can go way further with the 8, 16, and 32 terabytes if you would like to host that large workload on a single node and save on compute costs. As long as you can get performance that you need, you're absolutely welcome to do that, unlike other solutions that are offered on the market for MongoDB. And the last but not least is the less physical shards for the same workloads are enabled by these 32 terabyte. It's just a simple calculation, right? If you have a over 100 terabyte of workload, let's say 160 terabytes workload, and you can use that many nodes, like 40 nodes with a 40 terabyte industry standard one. It's a lot of compute, no matter how you look at that, to pay for. Even if you try kind of to decrease the number of vCores on a single node. And then if you go to 32, as you kind of increase the storage per physical node, again, it's a simple calculation. For the same 160 terabyte of workload, you just need 5 shards. So total number of vCores could be somewhat smaller for that configuration, delivering the same performance. And as usually, it's a balance. For some workloads, just more computer nodes would deliver higher performance thanks to parallelization of that
Mhm.
effort. Then they can go with a 10 nodes with a 16 terabyte, but still it is significantly less than 40 nodes with a 4 terabyte
And just so I
of shard.
understand, like you explained this earlier, but I, just for my own clarification here, the compute and the storage are decoupled from each other, right? So if you've got a workload that
Correct.
requires really high compute, you're going to need more shards to handle all of that processing, all of that IOPS that going in there, versus storage. I mean, you just tag the storage you need for that thing. And then I guess there's going to be an optimization where you want to keep the number of physical shards to the minimum necessary to run the compute necessary for that workload, basically, to get the right IOPS you want out of it. Is that, did I capture
Yeah.
that correctly?
Yeah,
Okay.
Mark, you got it right. So that's how it works, and that's how the underlying architecture and the storage is created, where compute nodes, so compute and amount of memory that is coming with this kind of power of compute is decoupled from the storage. So that's why there are kind of two knobs basically to turn. And for each workload, we understand it could be very different. If you don't need that much compute power for your workload, you can absolutely decrease it and save on these costs while keeping the storage as high as 32 terabyte per node and keep increasing the number of nodes. So it's up to 10 nodes today. So it's already hundreds of terabytes that we're talking here in a single workload.
I really like that you could really dial in what you need for the workload here. So that's very cool that they're not, that the storage and the computer are not pegged to each other. They can move independent of each other. So
yeah, that's true. So few tips on how to get the most out of your large storage, because when you select in a smaller storage, or it's kind of a single node, half a terabyte, even kind of less than half a terabyte, usually there are no special considerations for that. You can just select whatever compute kind of works and delivers you the performance. Could be relatively small compute, you're still kind of doing fine. With the large storage, very small compute is going to limit the IOPS on a VM level, and you wouldn't be able to realize all of the power that storage potentially can provide in terms of IOPS. So you would need kind of to think it through and then check our kind of docs where we're providing the matrix, which compute should be minimally selected for which size of storage to get the most out of the IOPS. The link is on the screen.
Yep.
But basically, as a rule of thumb, is that when you go with the 16 vCores, you can use up to 32 terabyte, and there are no limits. So 16 vCores M60 compute tier or higher is going to be working and not limiting for anything. If you go in smaller, then please check the matrix, and I put it here on the screen. That's basically what we have in the documentation. Plus, we have a number of additional tips and some guidance for how to think about and how to select the compute and storage on the page that I'm referring you to. But that's basically how it works. If you select the 16 vCores, you can go as high as 32. However, if 8 vCores is your selection, then you're going to get full IOPS, 7,500 of IOPS, only from 4 terabyte. And the 8 terabyte is going to be somewhat limited. So you're going to lose few thousands of IOPS if you go 8 terabyte and 8 vCores, for instance.
Yeah. Okay. Can you change it if you provision a size in a compute?
Yeah,
can you
absolutely. Because people, of course, make mistakes.
Yeah.
They may select wrong kind of compute and then realize, oh, wait a sec, I provisioned 16 terabytes and I have like 4 vCores, for instance, and it's going to be kind of a severely limited one in terms of IOPS. And then you can scale what we call scaling up the nodes, so kind of change compute dynamically.
Okay. Okay, cool.
So that's basically just the screen from Azure portal where we are looking at the configuration of the cluster. So first you're creating your compute. That's what we've been talking about. So those of you who used Azure Cosmos DB for MongoDB vCore, they're kind of familiar with this screen. And here you're creating kind of the storage. All of that kind of per node, per physical shard. The number of physical shards are down the screen. So here we're focusing on the storage. Up until recently, we were supporting just industry standard up to 4 terabytes. And now we have 3 new sizes that we've been talking about in preview. And in the coming weeks, they're gonna become generally available. So all of that is coming very soon.
Right on. Yeah, that's
Um,
pretty cool.
So for multi-shard, there is an additional thing that you would need to select to be able to get access to it. Currently, multi-shard configurations, 3, 4, and 5 shards are in preview. So when you're creating your vCore cluster in Azure portal, you just need to set additional checkbox, allow access to global distribution, because multi-shard is previewed together with the cross-region replication. And then in the configure screen, you would be able to see these kind of additional shards. So as I said, we kind of providing up to 10 shards. Depending on your subscription, you may see up to 5. Then it's just a simple request to Azure support to allow access up to 10 if you don't see all of them. So just to connect it to the screen that we were looking at before, this is the same cluster configuration screen where you're selecting your compute, then you're selecting your storage, all of that per one shard. You're selecting high availability or not. We'll talk about that in a second. And then you present it with the what we call advanced option, because again, if single shard works for your workload, absolutely go with the single shard and there is nothing else is needed. However, once you face the reality that you need more than one node, we have it covered. So here kind of the additional selection. That's kind of the multi-shard and a large storage. And I would like to switch now to a couple of fundamentals that go hand in hand with that, which is Inregion HA and cross-region replication.
Okay.
So for in-region high availability, we just seen it in the configuration screen. So we're basically looking at another part of what are other options that you can configure in your MongoDB vCore cluster. So it can be enabled and disabled for the whole cluster. One of the questions that people asking sometimes, can I enable and disable HA on a single node? It probably doesn't make much sense if only one node is covered, at least in most of the scenarios. So these features provided for the whole cluster, and the flexibility is that you can enable and disable at any time. You can do it at provisioning time or at any time on your existing cluster. So you can start with the experiments on the cluster without HA, and once you're ready to move into production, you enable the HA. There is no impact on the basically production cluster or any cluster whatsoever when you enable and disable an HA. All of that is done with those standby nodes that we're creating for the cluster to enable HA, and we will take a look at the diagram in a second on the next slide. It is available not only for multi-shard, so it's not exclusively multi-shard configuration feature. It is, of course, available for single shards, because there's a lot of production workloads that are running on single shards in MongoDB. It is synchronous replication that we're using for in-region HA, which means that whenever we need to do a failover, there is always current copy of the data on a standby node where we're failing over, and it means there is zero data loss. So wherever data was written on the cluster is there on a standby node always, and failover does not result in any data loss in any scenario. Well, and last but not least, once you enable HA on your cluster, you're also covered by 99.95% monthly availability SLA for your cluster, which is also kind of a nice
Are
benefit.
these, is the in-region zonal?
Yes, that's a great question. We're provisioning all of the primary nodes in one availability zone.
Yeah.
And all of the standby nodes in another availability zone. Of course, we're doing that only in Azure regions that do support availability zones, because as you probably know, some of the Azure regions, they just don't have availability zones, but it kind of goes by definition of availability zones in Azure.
Got it. Okay.
So now let's take a look at the HA architecture. So what's kind of under the hood and how we actually implemented it, so that you can see how it actually works, this kind of zero data loss. It's a busy diagram, so let's start to kind of unpacking it. So first of all, the whole thing is in one Azure region. There are two availability zones. Thanks, Mark, for asking this
I
question.
don't know how I did that. It's like magic or something.
That was good. So let's start with the application. So again, your application with the MongoDB client, it is blissfully unaware of all of the complexities on the backend. It just has one endpoint, so it connects to MongoDB database on this complex cluster as it would to any other MongoDB in the world, and just interacting with that kind of database. So this in AZ1 is cluster, the active cluster with again two shards. For simplicity, I just selected two shards. It could be any number between 1 shard and 10 shards. So these kind of two shards are presented again as a single database through one endpoint to the application. What's important is that once you say in a portal, I want high availability to be enabled, there is a standby node created for each shard. So this is kind of shard 0 standby, and there is independently shard 1 standby, which is exact copy of that physical shard, which means the same compute and same storage resources are just created in another availability zone. And then we establish synchronous replication between these two nodes. So each pair of the primary node and standby has synchronous replication running as long as you have high availability enabled on your cluster. So what does it mean kind of in a nutshell? In a nutshell, it means that when the application writes to a node, well, it writes to the database and then the actual write goes to one node or the other node. When the write is kind of committed on that node before application gets confirmation that the write is completed, we do in the quick round trip to its standby to complete the write there. So when application is getting confirmation, acknowledgement, like, hey, this write is completed, it means that it's already physically present on these two nodes. So if in that very moment something happens with the node, like wherever is the reason, it could be the node, could be something between the node and other infrastructure like pieces of networking components, something stopped working all of a sudden. It's less and less frequent, but it still may happen. This node becomes fully unavailable. Our service would detect it, declare it unavailable, and automatically switch to this node, absolutely transparently to the app. One possible kind of impact on the app could be while the switch is in progress, that there are delays because we may be trying in our service the requests that are coming from the app, but that's kind of the likely consequences of the switch, even if there is something in progress while we're doing the failover.
God, if say a single shard fails over, these fail over independent of each other. It's not the whole.
That's correct. So we don't need to touch the other shards. Imagine you have like 10 shards, right? If something happens just with one shard, and again, it's a separate physical node that is dedicated just to this database, to this cluster. There's no multi-tenancy, unlike, well, other architectures that we use in other kind of APIs. So here, this node is fully dedicated, so we can just completely discard it and replace it with another one and rebuild the standby.
Good. Does that happen just basically by itself? Is there kind of some self-healing?
Correct. Yeah, it's self-healing. So the moment we complete the failover, we start rebuilding the standby automatically. Correct. Of course, there are no miracles. There's some time required to rebuild the standby. However, our statistical models, they just showing that probability of the second failure happening on that node is very, very low.
Yeah.
It is like many nines in this percentage for this to happen. So in reality, we haven't seen that across multiple database services in a good number of years that we've been doing this observation.
Yeah, very cool.
Now that we kind of talked about the high availability, we have kind of some idea of the multi-shard cluster, some pretty good idea. The large storage is a part of the multi-shard clusters, in-region high availability. And now you will see that, just spoiler alert, in a second in another diagram when we'll be talking about cross-region replication. So basically, we just keep building our production solution by adding additional components. So hopefully all of that will kind of add up and then build in a coherent kind of picture of what we actually offer in here. So back to cross-region replication. What we have here is basically a replica cluster that we're creating in another region. So remember, everything that we've talked about to that point was in a single Azure region. Now we're adding an additional dimension, which is another Azure region. And there is an exact copy of wherever is the configuration of the cluster here, except the high availability, because we do not provide high availability on the replicas. So there is kind of no need to have it there while it is available for read only. One of the primary differences between in-region high availability and the standby nodes that we're running there and cross-region is the type of the replication that we use. For cross-region, because of the increased latency between the regions and this kind of journey over the internet for everything that is going between the regions, we're using asynchronous replication. Basically, it means that unlike in high availability, we're not waiting for the writes on the primary cluster to be committed on the read replica. Application is getting confirmation the moment when the primary region gets the writes, which means that there is, and often it is the case, there is a replication lag. So some data that is already written to the primary cluster hasn't reached yet its replica. There are basically two reasons why customers are interested in cross-region replication. There's disaster recovery part and there's read scalability, and they can be used together or kind of independently. There are different school of thoughts about that. But I would say that for majority of the customers, it's disaster recovery, first and foremost. Customers are saying, so we understand that outage in the region is happening infrequently and less frequently, that we in Azure keep working on improving that. However, how can I hedge my risks even for this kind of infrequent event? And of course, the answer is have copy of your data in another region and be able and be ready to use that region basically to switch to that other region if something happens with the whole primary region. So for that, we're providing a capability to promote replica region to read-write capabilities. Basically, there is a promote button in the portal that allows you to declare that replica open for writes. And then if your primary cluster is available at that point, then it would become available for reads. So basically, read write and then read rules are going to be swapped between the regions. That's the gist of the disaster recovery. And as far as connection strings are concerned, we're providing one connection string per cluster. If customers decide to use this one connection string per cluster, they can connect to primary cluster to do writes and reads, and to the read replica to do just the reads. However, once promotion is initiated, it would be on the application side to do the swap and basically change the connection strings. If that is undesirable, then we also provide a global read-write string that always points to the right region. So basically, our service is tracking the promotion event, and as a part of the promoted replica, opening it for the writes, the global read-write string is updated to point to the freshly promoted replica. So now application can continue the writes, and the reads using the global read-write connection string without any changes. So that's just to help with the automation. And the last thing to mention here is kind of the read scalability. So that's still kind of a thing. I keep calling it replica cluster and read replica cluster interchangeably on purpose because the read capability is there. The cluster is fully available for the reads even when no disaster is happening. So if there are a couple of scenarios that are here in play that are kind of worth consideration. Well, first, when the primary cluster is at risk of being loaded with the reads. Think about a dashboard with the thousands and hundreds of thousands of users that just keep refreshing this dashboard that is hitting the database, for instance. Then read replica is a very convenient way to remove this risk, and then the read replica is overloaded and not putting at risk the writes and performance of the writes that need to be done, or let's say more sensitive applications that can perform the reads from the primary cluster. And the second one, of course, is if somebody is in the region where the read replica is located, or is kind of closer to the region where the read replica is located, probably makes more sense to do the reads from that cluster just because it's going to be faster.
Yeah, makes sense. The replication, the asynchronous replication, I'm guessing this is just like an eventual consistency type contract.
Correct. In kind of using the terminology of the MongoDB RU, for instance, is going to be eventual consistency.
Right.
And now the promise diagram. So we keep adding the components as I promised. So now let's take a look what we have here. So basically here in region A at the top, we have a cluster. This is the primary nodes, like multi-shard cluster, and it has HA enabled with the HA standby here with the kind of 3 physical shards too, and the synchronous replication between them as we discussed. All of that is happening in one region. And the application can connect using the self connection string to that cluster or global read-write string, as I mentioned on the slide before. So they're kind of these kind of two things. And again, from application standpoint, it is still just MongoDB database. An application doesn't need to know. There's nothing to do on the application level for any of these complexities. Now that we're creating a read replica in another region, like region B, we have another copy of the cluster available for read. So there's another connection string for the app to read from that cluster, or for another app to read from that cluster, and a synchronous replication going from the primary cluster to that read replica. So now let's take a look what is happening after the promotion. Let's say for whatever reason, maybe we just decided to test it. We went to the replica and said, I want to promote this cluster. Now I would like this cluster to become available for writes, and this cluster would accept read-only role. So that's the after promotion picture, where we have physically they are still the same, the one and the other cluster. Now X read replica became available for reads and writes, and global read-write strings switch from that cluster to the read replica. Now it's in region B, and the X primary cluster now available only for reads. It kept its connection string. Everything continues to work. One important thing to mention here, as you probably noticed, so let's go back again before promotion, and now we kind of promoted the cluster. There is no HA. Because we do not support high availability on the replicas, there was no HA here. So once the promotion is completed, this cluster becomes a read-only replica and loses its HA. And if you need high availability on a freshly promoted cluster, you just need to go to the portal and enable it. So at this point, it's just done manually. And there are some other things like you may want to update your networking settings because they're configured separately for 2 clusters. And sometimes customers even doing it on purpose. They're saying, hey, I don't want those who is kind of hitting with this intensive reads the replica to be able to even access my primary cluster. So if networking settings are different on these 2 clusters, which is one of the possible configuration options, then you would need to go and update the networking settings on the cluster to match the ones that were before on read-write. And you can absolutely recreate this HA just, again, by going to the portal and using the toggle for enabling high availability.
Do you have to do it in the portal, or can you use Mongo shell type commands?
Yeah, that's kind of a good question. There is no Mongo shell support, but there are a number of things that we support as a programmatic management, including the HA enablement and disablement. So in addition to Portal, you can use REST APIs. You can use Azure SDKs. You can use Terraform, ARM templates,
Okay.
or basic.
So users can do it just through Azure Resource Management, basically.
Correct.
Okay.
So
That's fine.
all
I
of
think
the
most people are using ARM to do all that kind of stuff anyway,
yeah.
right? So, yeah. So,
I just mentioned it, for completeness of the picture.
yeah, no,
So all of the operations that we were talking about, I was referring to the portal as a more visual kind of mean of doing this management operation, but you absolutely can do all of them using the REST APIs and other methods that I just mentioned.
and how long does that failover, that switching take if you're going from
So it varies. That's actually a good question. When you promote a replica, the time that changes taken effect varies. Usually, it is just a number of tens of seconds.
Okay.
It could go higher. So the replica itself, of course, continues to be available for the reads. So it's just about opening it for the writes. And if this cluster continues to be available, like there is no full region outage, then it's also going to be continue to be available for the reads. Just at some point, the writes will stop being accepted, and at that point, the writes will be available on that cluster.
I'm
And all
guessing,
of
are you guys just do you halt the write so that the replication queue can drain and then you flip?
we're doing as much as possible. I
Yeah.
cannot promise that it's going to be the case in 100 cases. So there is a possibility of some writes to fail in some cases, but we're trying to decrease that chance.
Got it. So I mean, it's asynchronous replication. It's non-RPO0 is what you're kind of implying here.
Correct.
If you're failing over, and if you cannot, like, let's just say network connectivity is lost, like the region can't talk to anything. There's no way you're
Correct.
getting your data.
Yeah.
You obviously want your app up, right? So you're gonna accept an RPO greater than 0 just so you can get the RTO down.
From our observations, in most cases, we are able, Mark, as you described, just to hold it and retry it in the service,
Mhm.
and life continues. For the application, it's just a little bit of a delay, not such a big deal in most cases.
Yeah.
But there are some outliers. I would say it's a minority of the cases
Yeah.
when it could be just a little bit too long and a timeouts, and then it will require a retry on the upside, so detecting the failure. But that's anyway kind of our recommendation for any cloud apps, to have some retry logic on the upside
Yeah,
for
of
various
course.
cases, not only for promotion.
Yeah, makes sense. Okay.
So just quickly, because it's relatively simple and relatively straightforward. So what I was talking about, how to enable cross-region replication. So we looked at the checkbox for enabling access to the review for the global distribution before. It is the same checkbox for multi-shard and cross-region replication that you're setting on the basics tab. And then you have two options. You can create a read replica during cluster provisioning. That's the screen we're looking at. So you're kind of going through the provisioning sequence. You've done the basics, the cluster name, the subscription, the configuration that we talked about. Now you can just click enable on the global distribution tab, and you need to select a region. In this case, UK South. You can create cluster in any region that we support. We don't limit which region you can create replica in. And then you just need to give replica a name, which is also going to be used in a connection string. And that's basically it. You continue with the provisioning of the cluster, you get in the primary cluster and a replica in another region. If you're not ready to create your replica, that's absolutely a valid case. You just select disable here, which is selected by default. And then in your cluster, once it is provisioned, at any point you can go to global distribution blade and basically enter the same data, click save, and you're going to get your replica created at that point. And of course, you can drop it also at any point. So if you don't need a read replica anymore, or you want to create it in another region, you can always delete it and recreate it at any point. With that, I wanted just to quickly go through the big sections again because we covered a lot of different things today that kind of go together when you are trying to understand how to handle large workload on Azure Cosmos DB for MongoDB vCore. So we talked about how to create multi-shard clusters, when multi-shard clusters make sense, what exactly kind of the parameters of multi-shard clusters that are offered in our service and how they help you handle hundreds of terabytes of your MongoDB workload. Large storage was a large part in that picture where you can increase storage per physical shard in your multi-shard cluster up to 32 terabytes and 20,000 IOPS per shard. And then we talked about a couple of fundamentals that most of the time are a must for these kind of complex multi-shard hundreds of terabytes workloads, which is Inregion HA for production availability and cross-region replication for disaster recovery and read scalability. For all of that, I would say if you would like to learn more about all of it, you can start with the blog at the URL that is on the screen. So this blog is about multi-shard cluster, and it would guide you through the thought process and would also give you the entry point to a number of other resources.
Yeah, and I got the blog post up there as well.
Excellent.
Same URL, so people want to go and check that out, read more about everything here. They can start there, and then of course I'll put that other that doc back up that had the matrix on there and a bunch of other information as well for people to go and check out when they're trying to do basically kind of their planning in there for building sharding for these kinds of workloads. This is really cool. I'm just blown away. I mean, I guess I'm used to 50 gig shard sizes now for the Cosmos NoSQL server. So when I hear like 32 terabytes per physical shard, I'm like, man, it blows me away. And like you were saying, it's an order of magnitude greater than like the 4 terabytes you would see on kind of like a normal compute node for that type of thing. So that's just an enormous amount of data that you can put in there. And I just love, that you can mix and match the right compute with the right storage, dial in your workload to get the right performance, the right cost. And then you have these other goodies for, all the RPO 0 with the HA option there in region with the zonal HA. And then of course, being able to do those regional replicas as well. You guys are really dialing it in, and this is great stuff from you guys. So thanks, Nick, for being on the show. Absolutely. You don't have to ask twice, but I'd love to have you on for someone on your team to come and talk about the migration
I fully agree.
story there.
We should do it. We should do it.
There's so much good stuff that's been going on that front, and we got to get that story out, and we got to let people know just how much good stuff there is there to help them kind of plan and actually do these types of migrations to Cosmos DB for MongoDB. So, Nick, great having you on. It's been a long time. Thank you again for joining us on episode 99 for Cosmos DB TV. Maybe I should send you a plaque or something. Episode 99 on the show there. It's really great. We're getting close to 100 here, and I'm getting really excited. So thanks for helping us get there.
Thank you for having me.
All right. Hey, folks, thanks so much for joining us. By the way, I think I mentioned this last week. We've got a new samples gallery out. Come check it out. Oh, there's got to be like 80, 90 different samples in there. We've got docs and videos and tons of GitHub samples or repos with samples on there. There's PowerPoint decks. What else we got in there? I think that's it, but there's a lot of stuff in there. Come check it out. It's growing every day. We're adding more content on there, so come check it out at the Cosmos DB samples gallery. That's aka.ms, Azure Cosmos DB/gallery. Nick, thanks again for joining us, and thank you, folks. Next time it's episode 100. Make sure you check us out, and then we'll be going on from there into 3 digits of episodes. So, Nick, thank you again very much, and thank you everyone for joining us.
Thank you.